So I have some logistical things to deal with first. First of all, how many of you duck covered and held on this morning? One? Anybody else? Two? Three? Four? Okay, can you get their names? This is extra credit. Oh, yeah, right. Yeah, very funny. So as I'm sure, hopefully, most of you heard the siren that go off at 10:16 this morning. So this is an annual event. It's called the Great California. Is it Great California? I don't know, the Great Why, whatever. It's called the Shakeout. Why it has to be the Great California Shakeout is something I do not understand. But this is an annual earthquake drill that they have on the third Thursday of October every year. And this is actually from last year, the webpage from last year. I tried to get a copy of the webpage this morning, and of course I couldn't get to the website because the whole of California is on the website this morning. But they basically have agencies sign up. UC Berkeley signed up. So although you don't know it, you're all counted in this. This is last year's number, but whatever the number is this year, you're all counted as having participated in California's Great Shakeout. So I'm glad that out of the, well, I don't know how many people in this room, 150 of you in this room, that 3 of you actually did participate in the duck cover and hold on. But I'm pointing it out really because this is a great mechanism for you as individuals to use on an annual basis in the future to think about earthquake preparedness. Obviously, one of the things I want you to do as a result of this class is be aware of the earthquake problem and what you need to do. But it's something that has to be, you have to remind yourself, you have to update your plan, you have to do the next step, do one more thing when it comes to earthquake preparedness. And so hopefully, now you know what the California Shakeout is. When you come into contact with it in future years, you can use that as a reminder of, I took that earthquakes class one fall many, many years ago, and you can use it to just kind of make sure you know what your earthquake plan is. Okay? All right. Following that, here's the grade distribution for the midterm. The grades are all up. They've all been posted in vSpace, so hopefully you all now understand how to see your grades. You know what your grades are. And so this just shows you what the distribution of grades was. And so, the 14 bar here means a score between 14 and 14.5, just so you know. And so what I've indicated on here is approximately where the A, B, and C boundaries will fall at the end of the semester. Of course, it will be based on your overall score, and this is just the midterm score. But I just want to give you a sense. Everybody wants to know kind of how they're doing in the broad scheme of things. And so you know what your score is. You can see where you fall on this plot, and that gives you a sense of how you're doing in the big picture of things. Okay. Likewise, here's a similar plot, but for all of the grades so far. So the field trip report, the first 2 assignments, and the midterm. And this is what the distribution looks like. And again, this is where the grade boundaries will likely fall. All right. Any questions about that? None? Wow. Excellent. Okay, so then let's move on into today's material. So we're continuing in this sort of vein of how we interpret seismograms and characterize earthquakes. We talked about P waves and S waves. We talked about picking P waves and S waves and locating earthquakes. And today we're going to talk about magnitude and energy, so the size of the earthquake. When you're picking P waves and locating earthquakes, it's about where the earthquakes occurred and when they occurred. When we look at the amplitude of the seismogram, that tells us about the size of the earthquake, which we can describe in terms of the magnitude or the energy associated with the earthquake. Okay, so that's what we're going to talk about today. The whole of Chapter 8 is on this topic, so I encourage you to read Chapter 8 of your textbook. All right, so I wanted to start with this list by showing you this list. This is the list of the largest known earthquakes, or the largest instrumentally recorded earthquakes that we know about. And so top of the list is the Chile earthquake from 1960, estimated to be a magnitude 9.5 earthquake. Number 2 is the Alaska earthquake. We just had the anniversary of the Alaska earthquake earlier this year. That was estimated to be a magnitude 9.2. And then number 3 on the list is much more recent, 2004, the Sumatra earthquake, a magnitude 9.1. That was the earthquake that generated the huge tsunami in the Indian Ocean. About 250,000 people were killed in that earthquake and the tsunami that followed it. And so just want to sort of show you a little bit about that particular event. So this is a sort of tectonic map, and then the yellow dots are actually all of the aftershocks. Okay? So the tectonic situation here is that there is subduction of the Indian Ocean going on underneath the Eurasian plate right here. Okay? It's oblique subduction. The red arrows are showing you the direction of motion between the Indian plate and the Eurasian plate. Okay? And so there is oblique subduction going on in this region. What can we tell from this map of aftershocks? What do the aftershocks tell us? The geographic distribution of the aftershocks is telling us what? Yeah. Exactly, where the fault that ruptured was, right? So remember that when you have a big earthquake like this, you then have a whole bunch of aftershocks, and the aftershocks are all distributed around the main fault, the primary fault that slipped in the main shock, okay? So just by looking at this map of aftershocks, the star, so I didn't say the star is the epicenter of the main shock. Okay, so this is where the main shock started, but the main shock ruptured a portion of the fault that extends all the way up here, okay? Now, I realize there's no scale bar on here. However, what I can tell you, you probably can't read this. This is 0 degrees. This is 10 degrees. So 1 degree of latitude, this is 10 degrees of latitude. 1 degree of latitude is 111 kilometers. Always, everywhere. Only true for latitude, not for longitude. Okay? So if this is 10 degrees, that means that this is 1,100 kilometers. All right? So this earthquake started here, and it ruptured all the way up to here. So this is about 1,500 kilometers. Okay? The earthquake ruptured 1,500 kilometers. Right? The 1906 earthquake that ruptured halfway down the San Andreas Fault was about 400 kilometers. So this was 3 times as long. The length of the fault that ruptured was 3 times the length of that. So that's basically the length of California. More than the length of California. So this was a huge earthquake, right? That's why it's number 3 on the world's largest earthquakes list. This is a map that shows the seismic hazard for this region. And you can see that there's a fair amount of seismic hazard. The warm colors mean increased hazard. Cold colors and white mean reduced hazard. So do you remember India is slamming into Eurasia at 9 centimeters per year? We talked about that when we talked about plate tectonics. So this is all relatively low hazard. And the reason is that, of course, all of the earthquakes are occurring in the Himalayas, which is just off the top of this map. But that wraps around and continues down into this region. And then you can see that the sort of southwestern edge of Sumatra is also high hazard. And so this is because of the subduction zone. So this whole region is high hazard because of the subduction zone. So again, this is not a surprise that we had a big earthquake in this particular region. Now, this is an animation that shows the propagation of the earthquake. So actually, let me go back. So we talked about the fact that the earthquake epicenter was here, so that's where the earthquake nucleated on the fault, and then it ruptured this whole long length. So if it started here, it then propagated from this point outwards, and it propagated up to the north along this fault plane. So the animation I'm going to show you is just a time-lapse image of the rupture propagating along. And this is based on using the seismograms to identify where the energy is coming from as a function of time to create this image. So it starts down here at the epicenter, and it ruptures its way up to the north of the earthquake. Obviously, this is sped up, or 400 seconds, 500 seconds, okay? So it took about 500 seconds for this rupture to make its way from the epicenter up to the northern end where it then stopped. All right, so it's more than 5 minutes. Right, 300 seconds is 5 minutes. So this stuff just gives you a sense of how long these earthquakes take to last. These are huge earthquakes that we are talking about. Okay, and so I'm going to show you one of my favorite things. And this is a photo of it, but I need to give you a sense of scale by showing you the actual thing that this is a photo of. So what you are seeing here is a photo of this Pyrex block that I'm holding up right now. Okay, and what is inscribed in this little Pyrex block is not a little ship or a San Francisco Giants emblem that you can buy, stuff like that. What is inscribed in this block is the actual particle motion as recorded at a seismometer in Pasadena in Southern California for the Sumatra earthquake. All right? It's not, we haven't got to the cool part yet. What is cool about this is that this is real scale. Okay? I know you can't see. All I'm expecting you to see from what I'm holding up is the size of the block. You can see what's in it from this image. Okay? And so this is true scale. So this is the actual particle motion that was observed in Pasadena. And you can read the scale off the slide, but you can see that the total peak amplitude of the motion was about 3 centimeters. So in Pasadena, California, very close to here, so it's basically the same motion here, there was 3 centimeters of displacement associated with that earthquake. So as the seismic waves came through Pasadena, the ground moved up and down by about 3 centimeters. Does that surprise you? I can't tell, I'm just doing mumbles. Yes, no? That is unbelievable. I could not believe this, all right? Okay, I'm a seismologist. I mean, the fact that this is an earthquake on the other side of the globe, it's 130 degrees from Pasadena, California to where this earthquake occurred. 180 degrees is on the opposite side of the earth. 130 degrees is getting pretty close to it. But Pasadena moved up and down by 3 centimeters. So, do you remember the damage that was done in Pasadena? No? Was there any damage in Pasadena? No, there was no damage in Pasadena. So if the ground moved 3 centimeters, why was there no damage? Foundations? Better soils? It's not really the reason. Yeah? Sorry, say that again? No. This is, yeah. So the question was, was this motion deep in the Earth's crust? So this is recorded on a seismometer that's, a meter below the surface, 50 at the surface. Yeah. Sorry, yeah. Exactly. Okay, it moved 3 centimeters, but it took a really long time. So when we think about the damage in an earthquake, we think about sort of sudden shaking like this, right? That's what damages buildings. So it's shaking that has a sort of periodicity. The periodicity is how long it takes to go up and down. A periodicity of kind of like a second or less. That's what damages buildings in earthquakes. And if you felt the Napa earthquake, you felt ground shaking that wasn't really fast. It was sort of, this kind of motion, all right? The reason that this, although there was 3 centimeters here as well, not just in Pasadena, the reason it didn't do any damage was because it was very long, very low frequency energy, very long period energy. It took a long time to go up 3 centimeters and then to go down 3 centimeters. Okay? And so you can see that if you look at the seismogram associated with this, well, this is the seismogram from Pasadena. This is the vertical component seismogram, okay? So this is just the time history. It's the same seismogram. This is the vertical component, obviously, in that image, in that block I have. Okay, so this total peak-to-peak motion is the same as what's shown here, all right? Total of 3 centimeters. Here's your scale, 0.5 centimeters. But what you then have to look at is the time scale. All right, so if we just look at the time scale for it to go, all the way up and all the way down and back to where we started, it's at least one of these ticks, if not perhaps 2 of these ticks. If it's 2 of these ticks, then it's 1,000 seconds. Okay, so it took, tens of minutes or 10 minutes, more than 10 minutes, for it to go up and then to go back down. So it's very slowly moving. Of course, nobody felt it. Right? So the motion is just a very long period motion. Okay? And so that is the difference between big earthquakes and small earthquakes. All earthquakes create this high frequency sort of shaking type energy. But when you have a really big earthquake, you also create this very long period energy as well. All right? And so in big earthquakes, we not only have to worry about this high frequency shaking, which you only really feel close to the earthquake, you also have to worry about this very long period shaking as well. Okay, so I'm going to go down to number 4 on this list. This was the Tohoku-Oki earthquake in 2011, even more recently, magnitude 9.0 earthquake. Again, another similar kind of animation for the Tohoku-Oki earthquake. This is the epicenter again. And you can see that this time history looks kind of quite different to the other time history. First of all, it's a lot shorter. What you just saw was actually the main event. What you're seeing now is, in fact, aftershocks that occurred immediately after the event. So the total duration of this earthquake, which was magnitude 9.0, was quite a bit less than for the Sumatra earthquake. And you saw that it was kind of much more complicated. So that Sumatra event was this kind of beautiful, simple, linear rupture going all the way from the southern end of the subduction zone up to the northern end. And the Tohoku-Oki earthquake was a much more complicated kind of rupture, but it was also, still a very large magnitude event. So it still generated this very low frequency energy. Okay? So very big earthquakes, they generate very long period energy, and that actually causes skyscrapers to sway. So while Pasadena went up and down very slowly over a period of about 10 minutes, there were basically aren't really any skyscrapers in LA, I guess there were a few. But the buildings that were closer to the event, so the buildings that were in Tokyo, they did experience this low frequency energy, and that caused these skyscrapers to sway back because the periodicity, the natural frequency of a skyscraper, the natural frequency is the frequency with which anything wants to oscillate. Okay, so skyscrapers have a natural frequency that has a period of multiple seconds. And so the Tohoku-Oki earthquake caused some skyscrapers to sway. So here's a video of this. That's almost as cool as my Pyrex block. So again, this is not dangerous. For the most part, this is not dangerous. In fact, these buildings are designed to do exactly this. So modern skyscrapers are all steel frame buildings, so their strength and their structure is based on a steel frame that has some give in it so that it can sway backwards and forwards. And then this is sort of either concrete or stone cladding that is stuck onto the building. Of course, you have to make sure it's stuck on sufficiently so that when it sways like this, it doesn't fall out. Oh, now it's swaying much faster, you see. And so, if you look on YouTube, of course, you can find lots of videos like this. This is pretty significant shaking. And of course, there was some damage. And there's all kinds of stories about people who were in these buildings, obviously horrified, because these buildings, people literally getting seasick, because this swaying would go on for many tens of minutes. I mean, you can't get out of it. Well, you have to leave the building. But you're not going to go and get in an elevator while the building is shaking. So pretty terrifying experience for the people who were in it. But, these buildings are built to withstand this kind of shaking. That's the good news. Yeah. So the question was, is this mostly caused by the surface waves? So the surface waves actually contain most of the long period energy. So the answer is yes. It's primarily the surface waves that cause this kind of swaying, and that's because it's the surface waves that have this low frequency energy. Yeah, other questions? All right. Okay, so that was to kind of give you a little bit of background. When it comes to big earthquakes, there are some aspects of big earthquakes that are kind of different to small earthquakes. We're going to get into a little bit of nitty-gritty now about what is earthquake magnitude. What does it really mean when I say this was a magnitude 9 earthquake or magnitude 6 earthquake like the Napa? So this is just to remind you, William covered this when he talked about the San Francisco fire. Remember, these are the maps of the geology, this is the geology, and then the shaking intensity associated with the 1906 earthquake. And what you saw is that there's a correlation between, first of all, the type of geology, whether you're on hard rock or whether you're on landfill, and the amount of shaking that you have. And of course, there's also a correlation. This is the San Andreas fault going offshore here. And if you were very close to the San Andreas fault, you had stronger shaking, and as you get further and further from the fault, the amount of shaking decreases. So this is just to make the point that when we talk about intensity, the intensity of shaking depends on where you are on the map. So for one earthquake that has one magnitude, there are many intensities of shaking associated with that earthquake. So that's why magnitude matters. Magnitude is the measure of the size of the earthquake. So there is one number, one magnitude, kind of, there's a caveat to this that I'll come to. There's one magnitude for an earthquake. The intensity depends on where you're located. So that's the difference. That's the key difference between the two. So why do we need magnitude? This is just saying what I said. The intensity of shaking varies depending on where you're located and what the soil conditions are, but the magnitude is a single number for the earthquake. Now, of course, everybody has heard of Richter magnitude, and you can pretty much guarantee, this is a source of frustration, you can guarantee when a reporter comes on, because there's just been an earthquake in the Bay Area, they say, the USGS reports a Richter magnitude of X. What are the two errors in that statement? You know the first. I've griped about this previously. The first problem is the USGS. So the magnitude for earthquakes that are significant comes from Berkeley. The USGS may report it, but it's a Berkeley magnitude. But we'll move on. The second problem with this is that we do not use Richter magnitude anymore. Richter magnitude was the first magnitude scale. I'm going to explain to you what it is right now. However, today we don't use Richter magnitude. And the reason is that Richter magnitude is tied specifically to an observation on a specific instrument that was an instrument that was around at the time that this scale was developed, and we don't use those anymore. So there is no Richter magnitude anymore. So they're just reporting the magnitude. They don't know what type of magnitude it is, and they just call it Richter magnitude. Okay? So if you're ever talking to a reporter and they're asking you about the earthquake, tell them it's not the Richter magnitude. Okay, so what the Richter magnitude is and was, if the magnitude is a log 10, okay, so this is a logarithmic scale, of the maximum amplitude recorded on a Wood-Anderson seismometer 100 kilometers from the epicenter. Okay, so this is an empirical magnitude scale, empirical measure of the size of the earthquake, and it is defined as log 10 of the amplitude on a Wood-Anderson instrument located 100 kilometers from the epicenter. Okay, that is the definition of Richter magnitude. So when a reporter tells you that, you say, where's that Wood-Anderson instrument that you're using? We don't use them anymore. This is the Wood-Anderson instrument, so you can get a sense of the vintage from the photograph, which is black and white. These were this is one of the earlier seismographs. I'm blanking, sorry, on a date, the year for you, but this was at the beginning of the 20th century, early in the 20th century that this scale was developed. And this instrument, this is sort of a schematic of the instrument. The way that it works is that there is a wire that's under tension that runs through the middle of this. Okay? And then there is a mass that's in here. And when the earthquake occurs, and on this mass is a mirror, and when the earthquake occurs, this mirror starts to rotate backwards and forwards. Okay? And so what you do is you shine a beam of light on this mirror, and then you record the reflection of that beam of light on a piece of film to record your seismogram. Okay? So is this measuring the horizontal component or vertical component? Horizontal. That's correct, right? Because it's when it's swinging back and forward. But it's also kind of measuring it's complicated in that it's a sort of measuring a rotational aspect of what's going on, rather than the simple particle motion that we've been talking about up until now. But that's a detail, let's not worry about it. The point is it's an empirical relationship where you have a seismogram that's recorded. You can see the P wave arrival on the seismogram. You can see the S wave arrival on the seismogram. And then you can measure the amplitude. It's a little confusing. This is a horizontal line that's been drawn at the maximum amplitude that's in here. So this spike up here is the maximum amplitude. Okay, so we can measure the S minus P time, right, on this. This is obviously centimeters, but you can convert that into time. And then this is the amplitude measured in millimeters. Okay, so the amplitude of this particular seismogram is 23 millimeters on this specific device. That doesn't mean it was 23 millimeters of ground motion. That's why the magnitude scale is tied to this specific piece of instrumentation. Okay? Any questions about this? Yeah. Great question. The question was, so for this to work, if this instrument had to be exactly 100 kilometers away from the epicenter, then there'd have to be thousands of instruments just so that you knew that, so that you would have one that was 100 kilometers away from the epicenter. Okay? And the answer to that is that, so we know that the amplitude, so we're going to use this, so we're going to use the time to locate the earthquake, and we're going to use the amplitude to estimate the magnitude. So if we develop the empirical relation for how the amplitude decreases as a function of distance, we can then correct for the fact that this particular instrument, this particular recording, wasn't 100 kilometers away. Okay? So let me show you how you do this. This is obviously we don't do this today, but this is a beautiful device. This is how you determine the magnitude of an earthquake with a piece of paper. I mean, it's fantastic. Okay? This is what's called a nonogram, which is what was used to determine the Richter magnitude. And so this is the process that you go through. All right? So these three axes here are the nonogram. There's a distance axis, right? So the distance and the time, the S minus P time, are obviously related to one another. So this one axis shows both the distance and shows the S minus P time. Okay? And then over here on this axis is the amplitude in millimeters measured on a Wood-Anderson instrument. And once you've measured those two things, you can determine the magnitude, which is on this middle scale. Okay, so how do we do this? So the first thing you do is you measure the S minus P time on your seismogram. And so in this case, this is actually, I said this was centimeters, it's not. This is actually in seconds. This scale bar here is in seconds. So the S minus P time for this is 24 seconds. So you go to your nonogram and you mark 24 seconds on this axis here. 24 seconds corresponds to, 210 kilometers from the fault. Okay, second step is you measure the amplitude in millimeters, and the amplitude of this is 23 millimeters. So you come down here and you mark 23 millimeters on the amplitude scale. You then go and you draw a straight line between the 2 points you've marked on the distance scale and on the amplitude scale, and where that line intersects this magnitude scale is the magnitude of the earthquake.